And I'll ask all the same things. What is the current through the inductor? What is the voltage across the capacitor? What is the current through the capacitor? Okay, a very long time after the switch is closed, what is the current through that inductor?
Through the inductor after a long time?
Yeah.
Oh, it'll just be the 0.3 amps, right?
Exactly. It's I over R2. Because in the short run, the inductor did not allow any sudden change in current. In the long run, the inductor will act like a wire. Just like inductors at very low frequency act like a wire, inductors, after you've given them a long time to come to equilibrium, act like a wire. That doesn't mean there's no current through them. Wires carry current all the time, but there's no change. There's no rate of change of the current. They come to equilibrium. So the current through the inductor is just V battery over R2, which is 0.3 amps. di dt through the inductor is 0. So the voltage across the inductor is 0. All the voltage now is across that resistor, which is why I put the full 90 volts now across the resistor. How about the capacitor? After a very long time, what is the voltage drop on the capacitor and what is the current through the capacitor?
Current is 0, voltage is
Current is 0, which means the voltage is 90 volts. I've fully charged up that capacitor. The one way for saying, well, I'm not convinced the voltage is 90 volts. If the current through the capacitor is 0, that means the current through this resistor is also 0 because they're in series with each other. If the current through the resistor is 0, voltage drop across the resistor is 0. If this node's at 90, then this node's also got to be at 90. And if this node's at 90 and this node's grounded, then there's my 90 volt drop across the capacitor. So in the very long run, the capacitor is fully charged. The capacitor is now acting like a break in the circuit. So for the short time limit, I essentially treated the capacitor like a short. In the long time limit, I'm treating the capacitor like a break in the circuit. Now that doesn't mean its voltage drop is infinite, it just means its voltage drop is equal to the battery voltage, because it means the voltage across the resistor, that is 0. And still, Kirchhoff's loop rules apply as usual. If I add up the voltage drops around a whole closed loop, I had better get 0. All right, and again, the hardest case to analyze would be the middle case. If I'm near the resonance frequency, if I'm near 1 over root LC, I can imagine kind of oscillations taking place here. Also, I could ask, there's a time scale, there's an RC constant to charge that capacitor. There's a separate L over R constant to kind of get the current flowing at a steady rate through the inductor. But again, I would say, for the moment, if I want to keep the exam short,
Pun intended.
giving away too much, if I say one way for me to keep it short is not to worry too much about the grungy cases on these LRC circuits, but to say if there's one thing I want you to walk away knowing cold, it's how to do all the limiting behavior on the LRC circuits. And that will still give you something very useful to bring to the table as you start to examine the more quantitative behavior in Carlos's class. Knowing the limiting cases will always give you a good sanity check. So again, these could be good ranking problems. These could be good just flat out asking you questions like I've asked you here problems. Yes?
So will you be releasing some sample problems for like the inductive stuff?
Yeah, I'll put some more. I'll put some sample problems online. I will also be all day tomorrow, pretty much in the STEM Center. And let's see. At some point, I need to finish getting the test written. But would you like time on Sunday in the STEM Center also?
Time on Sunday.
Is that useful?
Are they open?
I don't think it's.
They're open if I'm there.
should be.
I don't know how much time though. Cause like.
What would be a good time on Sunday?
I mean, like, about how much time though? Cause like, I live pretty far.
Oh, okay.
Okay, well, besides Joe's commute.
The most important thing.
10 to 3 sounds good if you're available.
What's that?
10 to 3 sounds good.
10 to 3 on Sunday?
Yeah.
Okay, why don't we say, so Saturday I will be there kind of about 12 to 5.
Yeah.
And Sunday, 10 to 3 sounds good. Now, see, in both those cases, I will say if my migraines decide to be acting up and I am not able to see straight, I might put a very blurry looking sign on the door. I'll have the place open at least.
Okay.
But yes, if everything goes well, I will both have the place open and I will be in there. I probably will not be shooting videos because for whatever reason, shooting videos always, if I've got the weird visual effects, I don't know why, but something between looking back and forth at the little screen and the big board and something like that usually makes my perceptual system go all the more wonky and nausea-inducing. So so I probably won't be shooting videos, but I'll try to put some more written problems online. They should be, I mean, the stuff we've been talking about today should be a pretty good rundown. I will put more problems along the same themes essentially.
Yeah.
But again, there could be another one where you have to integrate across space to get the flux through a loop. I could try to do, at least one more where the B field's changing, at least one more where the area's changing, at least one more kind of turbine type thing where the angle's changing. But if you were to say, what are the things that you want to make sure you are ready to look at at a glance and ready to pick up and run, those would be the big themes.
So the biggest question I have for you is, it seems all the stuff that we went over today is reasonably familiar. Just some of the stuff that you're saying, it sounds like you're saying is not going to be a focus of the test, is the style of questions that Joe is posing for these RLC circuits.
If we had more time, I like talking about what would happen if I'm a little above resonance, what would happen if I'm a little below resonance. Those are also problems where I don't want you memorizing your way through it. I want you taking the time to reason your way through it.
Yeah.
And I just don't feel like that is what I want to have you devoting a lot of time to on Monday's test.
Okay.
It's if we had time for another 4-hour exam, I might do that luxury. On the other hand, I kind of felt like it's a grueling marathon to give you the exams that long in the first place. But that's not going to be my main emphasis on the LRC circuits. I will very likely limit myself to the limiting cases.
Yeah.
Because again, those are things that if there's, if we can afford a little bit of luxury on the time on the exam, I would rather spend it on induction and field type problems, frankly.
Perfect. Thank you.
Yeah.
I noticed there wasn't a lot of exam 1 material covered today. Is that just because we should have it cold?
Kind of a little of both. I am not going to ask you E-field superposition because that would be kind of a problem that's just flat out, here's a review problem from the first part.
Yeah. And
while that's an important part of the class, again, this is the exam where I've got to be disciplined on what I ask you to spend your time on. And I probably wouldn't do that. Now, on the other hand, there were times I said something like, oh yeah, instead of just giving you the resistance of this thing, what if I told you it was a copper bar and I told you the resistivity of copper and things like that? So, there are things we can do. I mean, hell, certainly just the fact that we apply Ohm's law to a lot of those induction problems and all that. So there's a little bit of material from the first section. I would say most, induction problems lend themselves much more to expecting you to be good at the second third of the class, the magnetic field part of the class, than they do at the first part of it. Yeah.
How well should we know the Maxwell equations and what the best way of preparing for the next round?
the Maxwell equation stuff really is just those are things that I want you to know. Those are not things I wanted you to prepare for the exam. So that's my parting gift to you of here are some cool things that you'll enjoy following up on in the future. But no, Maxwell's equations and vector calculus. Let's say this. What if I were to draw you this set of fields? E fields or B fields?
B.
Yes.
What do you think? E fields or B fields?
Yes.
B fields.
E fields, they have
B
divergence.
How can you tell they're E fields?
There's divergence.
Oh, it's a
You're
dipole.
going from the source.
There's a source and a sink.
It looks like there's a source and a sink to these things. I mean, unless something like is really going on at small length scales here, there's, oh yeah, no, there's going to be a little solenoid there and a little solenoid there. If this is kind of a pretty good, illustration where I haven't hid any interesting information, definitely E fields, because which of Maxwell's equations are they disobeying if they are E fields? If they're B fields, I'm sorry.
The divergence of the B field is 0.
Yeah, that is, this looks to me like this is a region of positive divergence. You're not supposed to have positive divergence for the B field. This looks like a region of negative divergence. Yes?
Could you have a solenoid that's in between those upper lines and those lower lines and that ends right before?
I would have to kind of have, well, I don't know, I could do something like this. I could put a little solenoid here. In fact, I could do a solenoid that actually connects, well, no, I can't do that. Could do a solenoid.
From like one big one that starts on the right side and goes to the left side so that the magnetic field line can go up and around over the solenoid and then through it.
Yeah, I would still have to kind of maybe have little guide things here that kind of squirrel the field around that way.
Mm-hmm.
I mean, if there's a lot of small scale information I've left out where the fields are bending sharply and all this kind of stuff, I could probably, get away with somehow creating a B field that's got that behavior. I say that only because I've drawn so few field lines. If I start drawing more of them, as soon as I've done something where you say, no, I can actually tell, I'm going to draw myself a little Gaussian surface. And I can see that the net flux out the surface of that Gaussian region is non-zero. Then right away I've said, okay, that's a field that is not divergence free. That's a field with some divergence to it. Since I was only drawing like 4 field lines, I could probably get away with saying, but then I fill the space in between them with all this other stuff, and I could end up making that a divergence-free field. But no, if I was saying that those 4 field lines are kind of showing you most of the important information there, then you'd say, well, hell, I mean, let me just do this. I just drew a Gaussian surface. It looks like the net flux through that surface is non-zero. The only way it couldn't be if I said, well, I didn't tell you that over here there's other field lines coming in like that. But again, as long as I'm saying, no, on the scale I'm showing you here, I've given you all the important information, then you can say right at a glance, this is the divergence theorem. The divergence theorem tells me if the net flux of a vector field out some surface divergence theorem tells me whatever I get when I calculate the net flux of a vector field out of some surface, that's equal to the integral of the divergence of that vector field through the interior there. On this one, I'm seeing a net flux of field lines out of that green surface. So that means unless I've hidden something like there's other parts of the green surface where I didn't tell you there's field lines coming in, then no, that's not a divergence-free field. That is a field with positive divergence on that left-hand region, negative divergence on this region over here, which means that either it is not a B field, or we can announce the discovery of magnetic monopoles, and then it doesn't matter what anybody's grade is on the test, they'll get the Nobel Prize. So this would be something that definitely violates that second one of Maxwell's equations. What if I told you that this next diagram I'm going to draw is a static field situation? None of the fields are changing with time. And I tell you that the fields are looking like this. Let's see, what did I say? Field lines are looking like that. And none of the fields are changing with time. Did I draw an E field or a B field there? Definitely a B field. Which one of Maxwell's equations would it violate if I tried to claim that it's an E field? And again, I give you the additional information that none of the fields are changing with time.
The curl B field should only match the derivative of B.
Exactly. Anytime I've got a, just like I said, anytime I can draw a Gaussian surface, and if you do a surface integral of the field, of the flux of the field through it, if you get a non-zero answer, that means you've got a non-zero divergence. Anytime you draw an Amperian loop and you get a non-zero circulation around that loop, that means you've got some curl to that field. So this field definitely has curl into the board or out of the board in this region here? Out of the board. Curl into the board in this region. If I had a changing magnetic field, I might be able to get away with saying that guy's an E field. But if my magnetic field's not changing, the curl of E should be zero. The curl of that field is not zero. That one definitely violates that third of Maxwell's equations there. I would say that style of problem maybe as one of, the conceptual problems near the beginning of the exam. I don't know. What do you guys think? Does that sound like too big of a leap from what we've said so far, or does that sound like that fits pretty well with what we've been talking about?
Could you give us the equation in sensibility?
Yeah, certainly. I'll put Maxwell's equations on the equation sheet anyway, just because, in a way, they're a wonderful cheat sheet. You'd say, if I'm just kind of brainstorming, trying to figure out how to do a problem, I could be searching the equation sheet for Gauss's law, or I could just say, this is my reminder that Gauss's law exists. Maybe getting Gauss's law from the vector calc version, maybe I also want to kind of look up the more mundane little flux of E field through the surface version. But this reminds me Gauss's law exists. This reminds me Faraday's law exists. This is kind of a very compact way of saying, man, my whole understanding of this entire class comes down to those four equations. So I'll put them on the sheet for their cultural value, if nothing else. But yeah, if I gave you those equations and I started to say, which of those make it impossible to interpret this diagram a certain way? Again, to me, that's a fair use of Maxwell's equations. If I was starting to say, oh yeah, we gave you all those vector calc identities, divergence of the curl is zero. That's an easy enough one to do. Curl of the curl is the minus the Laplacian plus the gradient of the divergence. No, that's we spent too little time doing those, and we weren't even really trying to get to the point where you were using those as part of your problem-solving technique. That was more just preview of things to come. Okay, anybody still not up to date on TBA hours?
I think there's a few students that are.
There's a few people who weren't here today, but
I sent them to you earlier.
Can you
Well, I think
reattach them to
this is-
just one
What's that?
email?
I think
Would
some
that be
of them are not in the
possible? Would you have time to do that?
Well, no, but as I'm looking through here, there's people who
I'll do that
are in
as
the
soon as we leave.
class
As a matter of
and
fact,
were
can you
not
stick
here
around and
today,
try to talk to her really quick? And then you and me
Yeah,
should
for
chat.
the most part, that could be a very
Yeah.
small list of people who I need to ambush with that thing on Monday, which is a workable project.
What about people who dropped the class? Because I noticed there were a few sheets like that.
If people drop the class, then we don't owe Norma those numbers. But yeah, anybody who's still in the class, we need to make sure that we get those to Norma. She was asking me for them today, so I was saying, okay, well, I'll get you most of them today. But if there's somebody who I don't see, it might have to be Monday. So, all right. Are we good?
Yep.
Okay, so I will see you in the STEM Center tomorrow. I will try to think up some more problems to post today. Again, I probably will not be shooting videos just because my perceptual systems are acting up to the point where I don't think I can shoot videos. But if that clears up, I might shoot some videos also. So.
Yeah.